Okay, so in this video, we're going to go over yet another property of Fourier transforms, and that property is called duality. Okay, and this is a pretty cool property. Sometimes when people first see it, it can be a little confusing, but we've actually already seen some examples of this property without knowing it. Okay, and you'll see what I mean after we explain what it is. Okay, so let me just first write the two formulas we have for Fourier transform. This is the inverse Fourier transform formula. Okay, and then we also have our Fourier transform formula. And if you look at these two equations, okay, the longer you look at them, the more similar they start to appear, right? In both cases, we have an integral, and we're integrating the other function, okay? In the inverse Fourier transform, we're integrating the Fourier transform. In the Fourier transform formula, we're integrating the function. And they're both being multiplied by complex exponentials. Of course, in one of them, the exponent is positive, and one the exponent has a negative sign. Okay, and then here we do have this extra 1 over 2 pi constant, but you can see they're pretty similar. Okay, they're pretty similar. And even in a lot of the properties we've seen so far, okay, we've kind of seen that, for instance, in the convolution multiplication property video right before this one, we saw convolution in time was multiplication in frequency, and multiplication time was almost convolution in frequency, but with that extra 1 over 2 pi factor. But you can see kind of this, for lack of a better word, duality, that's what it's called, okay, between the Fourier transform pair I have in time and frequency, and then what happens if I sort of switch that. Okay, and this duality property makes that precise. Let me write it down. This property is called duality, and here's what it says. Okay, it says, move this down a little. If f of t and f of omega are Fourier transform pairs, then, and here's what that switching meant, what happens when I look at my Fourier transform function as a function of time? Okay, what happens when I treat this function of omega and just say, let me change the axis label and say, what if that was a function of time? Okay, then what would the Fourier transform of that function be? And it turns out it is 2 pi f of negative omega. Okay, so this, again, like I said, it can be a little confusing when you first see it. Let's go over it one more time. This is what I was hinting at earlier with this switching idea. If you have a Fourier transform pair, what happens if you take the Fourier transform and switch it to be a time function? Okay, then what is the Fourier transform of that resulting time function? And it turns out it is 2 pi times f of negative omega. Okay, so let's try and prove this. It's actually pretty short. Let's just look at the Fourier transform of this function. Okay, Fourier transform of f of t is this. Okay, I'll maybe just write that. This is the Fourier transform of f of t. Okay, and we want to see, does that Fourier transform equal this function? All right. So what can we do? Well, the first thing I'm going to do, okay, is I'm going to integrate or write the integral. Okay, I'm going to keep all this the same. And then I'm just going to write this as e to the jt negative omega dt. Okay, I just took that negative sign and I sort of switched the omega and t and I grouped it with omega. And now I'm going to multiply and divide by 2 pi. And I get this. And now what is this? What is this function? Okay, well, let's compare it. What does it look most like above? Well, it looks most like this, right? So I have 1 over 2 pi, I have an integral, and then let's see where the integration variable omega appears. It appears right there, and it appears right there. Where does our integration variable t appear? It appears in the exact same two places, there and there. Okay, so the role that the integration variable is playing up here, omega, t is playing the exact same role. And as we know, it doesn't matter what you call that integration variable, okay, as long as it's doing the same job, and in these two cases it is. And so here, where is my, I'll even color code it, how about that? Here's my argument, that's where my argument appears. And here's where my integration variable appears. Now let's do the same down below. Here's where my integration variable appears. And we're taking the Fourier transform of this function. And so the argument we should want is something with omega. Well, there it is. So you can see that these two equations are doing the exact same thing, okay? This is just f evaluated at that yellow argument of negative omega. That's it. That's it. And that's the end of the proof. It's 2 pi f of negative omega. Okay? So you got to make sure you keep all your variables straight and understand the role of each variable in all of these expressions we're writing. But at the end of the day, it's not too difficult of a property to understand. You have a Fourier transform pair. What happens if we want the Fourier transform of this resulting function of omega, but treat it as a function of time? Turns out you get 2 pi f of negative omega. Okay, but because this can be a little confusing when you first see it, let's do some examples. And you'll see that we've actually already seen examples of this duality before. Okay, so we saw that rect of t over t naught, we saw that that had a Fourier transform t naught sinc of omega t naught over 2. Okay, we saw that in the rect and sinc Fourier transform pairs video. So now let's see what we get by duality. Okay, so this is our top Fourier transform pair. Now I'm going to use duality and say, all right, let me treat this as a time function. I'm going to look at that function of time instead of omega. What do I get? Well, t naught, that's just a constant. And then I get sinc of t times t naught over 2. I just plugged in t instead of omega. And that Fourier transform has to be this function of negative omega times 2 pi. So we're going to get 2 pi rect of negative omega over t naught. Okay. And duality says that is a valid Fourier transform pair. Okay. Let me just clean this up a little bit. This is 2 pi rect. Well, rect we know is an even function, so I can just get rid of that negative over t naught, right? The rect function, it doesn't matter if I look at it of omega or negative omega, it's symmetric about the vertical axis. So I can clean that up a little bit. I'll just write maybe this is because rect is even. Okay, so now this is telling us a new valid Fourier transform property where the function of time is actually a sinc function. But if you remember, we actually already saw that. We had to prove it. We proved it again. Okay, we proved that second property. First, we proved this Fourier transform pair. Then we did all the work to prove the second one. Turns out with duality, we just skipped all that second work because if we just manipulate this equation a little, we can make it look exactly like the pair that we know. And all we have to do is take omega naught to be t naught over 2. Then what do we get? Then t naught is 2 times omega naught times sinc of t times what? Well, times t naught over 2, that's just omega naught. So sinc of omega naught t. And over here, we're going to get 2 pi rect of what? Well, t naught is 2 times omega naught. So omega over 2 omega naught. And now we know that the Fourier transform is linear, so I can divide both sides by 2 omega naught. And what do I get? I get sinc of omega naught t is a Fourier transform pair with pi over omega naught rect of omega over 2 omega naught. And sure enough, you can check your notes, but this is the exact same as we derived before. But there we had to use the inverse Fourier transform integral. Okay, so this is kind of a much easier derivation just using duality. Okay, and we get the exact same property we got before using an integral. Okay, so duality can be pretty cool. And we've seen, if you notice, kind of a lot of the Fourier transform pairs we've done have been paired up into, you know, a function of time. Then we look at what's it like when that function is a function of frequency. Turns out all of those are kind of duals of each other using this duality property. So let's see another one. This one's a little simpler. We saw delta of t at Fourier transform 1. Okay, so by duality, what can we get from that? By duality, we look at this, instead of a function of omega, we look at it as a function of time, but 1, I mean, omega doesn't appear anywhere. If I make that a function of time, it's still just 1. And then what do I get on the other side? I get 2 pi times my original function of t, but when I plug in negative omega. So I'm going to get 2 pi delta of negative omega, but we know the delta function is even, right? Remember, it's just the limit of those rect functions, each one of which is even. If I take my delta function and I flip it across the y-axis, nothing changes. So this is just 2 pi delta of omega. Okay, and so what can I say? Just to make it look exactly like the property we had before, I'll divide both sides by 2 pi, and we get 1 over 2 pi as Fourier transform delta of omega. And this is, again, something that we saw before, but we use the inverse Fourier transform integral to get it. This is the same as we derived before. Okay, so you can use duality in a lot of cases to take one Fourier transform pair and get a second one for almost for free. All right, let's look at one final example. And this is going to be one that we have not seen. So, well, we saw the original Fourier transform pair, that e to the negative at times the unit step function at Fourier transform 1 over a plus j omega. Okay, so we did see that, and this was when a was positive. Okay, so this is a decaying exponential. So what do we get by duality? We'll get a brand new Fourier transform pair that we have not seen before. So for instance, if I had asked a question, what is the Fourier transform of 1 over a plus jt, right? You might have to do some sort of integration to get that before we knew about duality, but with duality, it's very simple because this is just this function of omega, but now a function of t. So we know its Fourier transform. We know its Fourier transform should be 2 pi times my original function of t evaluated at negative omega. So I'm going to get 2 pi times e to the negative a. But everywhere I see a t, I'll plug in a negative omega. And now I'll just clean this up a little bit. This is just 2 pi e to the a omega u of negative omega. And again, this is still when a is positive. So what does this look like? It looks like this. So this is just an increasing exponential, but this unit step makes it 0 whenever omega is positive. And so it just is an increasing exponential, but that stops at 0. And when omega is 0, this is right there at 2 pi. Okay, so that's what that function would look like. And we got this Fourier transform pair almost for free. We just used duality applied to a Fourier transform pair we derived earlier, and we get another one. Okay, so duality can be very useful. It's just a pretty cool property in general. Okay, so hopefully these examples help you make more sense of it. And that's all I had for this video. I'll see you in the next one.